All right. It's still unclear that uh, we're going to be able to make this thing work correctly. Uh, but we will try. And I guess theoretically people can chat now. If people have anything to say, we got a couple of people apparently showing up. Yay! Hi, folks. Thanks for coming. Uh, um, and um, if I got all the audio recording, all the audio streams routed in the correct direction, I know, in fact, I haven't because I'm hearing my own voice in my headphones, which is great. Step by step. So, otherwise, I think uh, um, might be more or less ready to go. So we will hang around um, and wait for the top of the hour and then see how much I can get through this without completely wiping everything out. Uh, um, I've got a bunch of new stuff. We shall see. Refill my coffee cup here. Something. Let's see. That's a nice trap. If I try to make sure these headphones are set, I'm liable to turn on some playback somewhere. Okay, let's not do that. Mm. that. We'll talk about it in a second. Hi, folks. We're back live for the third time, I think. Hopefully it'll go a little bit smoother as I gradually figure out how to all do this stuff. So today I want to talk about failure, and not just doing it, although I have plenty of that, but avoiding it and the consequences of that as well. So, all right, let's just get into it. All right, so what were we just looking at? It was what I'm calling level 2 plate. What is level 2 plate? Well, of course, it's plate that's made out of other plates. If a normal plate is made out of individual atoms, a level 2 plate, each what had been an individual atom, is now a whole subplate. And what we were seeing in the opening demo is the L2 plates were kind of fighting with each other about space, and so they were the L1 plates, the plate plates that we've been using for the last couple of months, were blowing up because they were seeing inconsistencies with each other. But then the L2 plate was healing up by reseeding new L1 plates within it, and yeah, it didn't. It's not working very well yet. Just for example, so these plates here, they were originally surrounding a little atom deck, from like 3 months ago or something, and the atom decks were dying for reasons I don't understand. But furthermore, the level 2 plate surrounding those things was supposed to be a 3x3 level 2 plate, so it should have had 9 atom decks, each of them surrounded by this new L2 plate stuff. And it's clearly messed up, and they're going all over the place. I don't know why that's happening as of yet. This is all pretty new. This stuff down here, these are ASCII plates, the same things that we're using in the Psi demos to display the function value scores that are coming back. That's also supposed to be 3x3, and that actually does a pretty good job managing to stay 3x3, except it gets invaded by the cancerous little plates. So very early, lots of problems. And why build L2 plates at all? And the idea is to embrace failure. And let's circle around to this. So there's this philosophical question, like, is our universe a simulation or is it real? Put the actual philosophy parts of it aside and just say, from a practical point of view, what it looks like to me is that in a simulation you can control the failures. You might not. You might make life difficult for yourself, but you don't have to. So there's always a slippery slope towards just having nice errors. And the serious question is, when you're with reality, you have to deal with the actual errors that you've got. And so, we're talking about robust first computing here, right, for ages. And that leads to this fundamental question about robust to what kind of errors. Because, when you're focusing on correctness, there, at least in simple cases, it's clear what correct means. And once you hit correct, exactly down to the bit correct, then you're done. And now you can focus on efficiency, and that's our traditional computing story. But once you admit that there's going to be underlying failures, the hardware's not going to be deterministic, you're going to have to deal with something. Now you have this fundamental question. You say, well, okay, but what kind of errors does my robust first computing need to be able to handle? And the answer is, well, it needs to handle whatever kinds of errors actually occur, but that couples the abstract computing to whatever physical implementation you may be dealing with. And implementation 1 might have different kind of errors than implementation 2. But in general, across implementations, my experience is there's nice errors and there's nasty errors. And nice errors are small individual pieces cleanly vanishing. Poof, gone. And the nasty errors are when things, like they don't completely disappear, but they get corrupted internally. And, rather than just, becoming empty space or disappearing entirely, it turns into a twisted version of something that actually makes sense, something that will trip you into trusting it to actually exist. So, for our purposes specifically, what about tectons? The key aspect of the plate tectonics, that number one, an individual plate is tightly coupled, that there's stuff that can depend on coordinates and sizes inside there, and we've gotten a lot of leverage out of that. But in addition, we have the ability to make it movable and growable by passing tectons through it to move it all one the other direction, or to leave a new line behind and have it get bigger. Well, what happens if we get a tecton failure in the middle of a plate? And, I've thought about this quite a bit. And fundamentally, the answer is the plate has to die, because, in fact, the way tectons work is the plate, as a tecton moves through a plate, the area around the tecton is essentially under local anesthesia. That's the way we've designed it. So, if you see a tecton, you just fall asleep like one of those sleeping goat things. And as a result, you never notice that parts of the plate on the other side of the tecton, in fact, are inconsistent with you, because the part that's behind the tecton has already had its size or position updated, whereas the part ahead of the tecton has not. And so the fact that the tecton causes the plate to go to sleep as it moves through is what makes the trick work. But now, what if the tecton, gets a failure that means it's gone, or a piece of it's gone, or the whole thing unwinds? Now we have this whole fracture down the middle of the plate. What are we going to do about it? And I've thought about this a lot on and off, and I've thought about this a lot in the last couple of weeks. And for sure, we could maybe armor the tecton harder. It could possibly be a two-level row moving through, although that causes other problems, or some various forms of additional redundancy to help tectons avoid evil Kirk failures, where you end up with a gap in the tecton line that you don't know where to put it in. Should I heal it down here, or heal it over here, or heal it here? It makes a difference. Or worse, now we have two, the good Kirk and the evil Kirk on the same line, and we need to decide what to do about it. In any event, it seems that because we were counting on the plate being a relatively area of consistency, if there's a tecton failure, the whole plate has to die. Whereas L2 plates made out of L1 plates, so it's the L1 plate. The tectons are not moving across the entire L2 plate. The L2 plate does not move by tectons. The L2 plate moves, if it does, once we get it debugged, by having tectons move through the individual L1 plates inside, so the whole thing can kind of oogie along. And that means if there's a tecton failure, it's going to take out a single L1 plate, like a loss of a site in the level 1 plate, in the regular plates that we've got. And so the L2 plate is designed to heal up by looking from the neighbors and saying, oh, look, there ought to be a L2 plate there because I'm level 2 coordinate 1, 2, so there should be a 1, 1 L2 plate above me. And it goes ahead and seeds one based on the contents of itself. And that's kind of weird, and it requires some thought on what you put in an L2 plate, but that's okay. And it heals up. So that's the key. And what that means is the small is beautiful. That whereas before we had been thinking about, the plates, the regular L1 plates that we've been dealing with, the way that I tend to implement them, as far as the bit budgets go, they tend to top out around 125 by 125 in terms of number of sites. And, you could imagine wanting to go much, much bigger. But that is already something that if we have a weird failure, a real tectonic failure, you lose 125 by 125. That's going to take a long time to recover. You have to rebuild from whatever that thing was doing. Whereas by saying we're going to limit ourselves to smaller plates and force us to move to level 2, where the individual plates are the sites are going to die, but we're going to communicate between them, they're going to heal up. Small is beautiful. So that's the reason for the L2 plates. We just got to get them working a little better. All right. Let me switch cameras here. All right, we've got our desktop 3x3 grid. I'm going to actually boot it up from cold here, since we haven't seen this in quite some time, and we've had some new folks joining the channel that may never have actually seen this at all, or certainly haven't seen it live. And the boot process, it still takes 90 seconds or something like that. But we can actually, let's see, can I do this? No, not that one. Not that, there, that's the one we want. So we've got the serial cable plugged into the middle of this ring, and so we can watch the thing booting up, and this is just a, typical, insofar as anything is typical, Linux boot process. Let's go back to, all right, so we'll see this once these guys start to heat up, when they get far enough into the boot that they can light up the screen. Then we'll get going. So there we go. So the screen comes up. Once the screen is up, then the MFM T2 engine is getting started. This is actually just a splash screen. Now the engine is going to start. And come on, you can do it. Oh, there we go. Okay. And we are running a new version of the cache traffic stress tester that I wrote way back when, to try to trigger those problems that were happening very intermittently on the grid as a whole. So here we are, and we can look at the tile now. I have terrible problems. I'm just using one of my webcam to shoot this, and it looks awful. We can zoom in a little bit, but it still looks awful. So I apologize for that. We've got to figure out a better way to record these things, but step by step. All right. So let's do one demo little here. I'll go back to the overall view. So suppose I have this tile just crash. I'll simulate a crash myself, and we'll see what happens to the rest of them. All right, so they're user-requested failure. That's the only kind of failure that we consider acceptable. And the engine automatically restarts. We saw that the neighbor closed the connection, and now it's opening up again. And you can see that the connections northwest and southwest have closed, and now they've opened again, and it all recovered fine. So that seems great. But the only reason that worked was because there was nothing going on in the universe. So if we actually seed the universe with a cache traffic stress tester, which we will do, boom. Okay, the way the cache traffic stress tester works is it fills, every time we get an event, we essentially take all of the sites that we can reach, the 40 sites that we can reach, and increment a counter in all of them, which forces the underlying MFM T2 engine, if the event is near an edge, it means it's going to have to transmit the maximum amount of information across to the neighboring tiles to let them know that all of these sites had changes. So now, if we try to do the same thing, if we, crash this tile, well, first off, here, look at this. So now when we have, you can see the traffic going through here. It's really pounding a lot. But here we go. Now we'll crash it. User requested failure. Ba-boom, ba-boom. There you go. Nice, huh? We took out the entire grid. And the reason is, as we've talked about on and off in the past, is once we have a bunch of events in progress, in order to get whatever little efficiencies, well, that's what it is, that we can have, each tile has the ability to have like 16 or 32 events going simultaneously that involve neighboring tiles, and so they wait to get packets that are labeled for them until they can advance that event, and once it's done and the cache has been exchanged, then it gets committed and so forth. And once it works fine, and this is an advantage of the fact that an event window is so circumscribed. It means we know that as long as the changes fit inside this event window, we can have a whole bunch of other ones going elsewhere, and there's no interference between them, as long as something doesn't go wrong in the substrate, as long as packets don't get lost or a tile disappears. But once we had all that stuff going, as we did, let's go back to sites, display sites. Now we're doing the flash traffic commands. This is where we send traffic to the grid that tells everybody to do it using the special flash traffic channel that we implemented. And now once again we can seed the stress tester, and off we go. So the point is when one of these guys crashes and all these other ones have dozens of events partially in flight, they don't know what to do about it. And they don't know what to do about it because I don't know what to do about it. What it all comes down to is that we are going to have user visible failures, where user means the Ulam programmer level, where the Ulam signs up to say, I'm going to try to provide you best effort deterministic execution. If your event starts and you're there and you decide what to do and you make your changes, the underlying engine will make its best effort to make sure that those changes get distributed consistently to everywhere they need to go. And the challenging part is when it needs to go inter-tile. And we've got that working lots, but we do not and we cannot have it working 100% of the time, because the damn neighboring tile is a separate device. It can be pulled out and dealt with separately. So there will be failures, and they're going to have to propagate up to the user visible program level, and we don't have any semantics for that. We don't know how to tell the Ulam level that, sorry, I promised it was going to be deterministic. It's not. So that's where we were months and months ago, and that's where I went and just left it. Because it's not like the tile is so important. The tile is in service of the sites, and we would love it if the sites could always have guaranteed success, guaranteed deterministic events. But we can't guarantee that. We know that. So the goal for this update was to get my head back into the tile code and deal with it and try to start mapping out how we're going to decide what to do. And when I started 2 weeks ago, I was thinking that the work for me was going to be to say, look at the Linux kernel code and the communication processor code and figure out where the bug might be. But then I gradually realized that's really not it. What has to be decided is how to present failure, how to embrace the failure and present it to the next level of the software in whatever form will do the least amount of damage to them. And that's what led to me making the L2 plate, to say, we've been sneakily, because we've had deterministic events, we've been having the plates getting bigger and bigger and bigger, doing more and more stuff in it. We feel like it's really cool. But now, here comes reality, here comes the grid saying, okay, there's going to be failures that are going to cause entire plates to blow up, and they're only going to blow up because we wrote software. And this is part of what's been in place from the beginning. There's the 2 death bits inside each element of plate that says, when something's gone wrong, take out the whole plate, take out my subplates, take out the super plates. 4 different combinations of how to die. That has been key to understanding what's going on. All right, so let's leave this for now. Have we got time? We're taking up a lot of time. We can go back. over here, can I maybe show you a little bit about, okay, yeah, let's just real quick. So now we are talking to the middle tile on this thing, and I wrote a new program this week. T2 tile, base, apps, preview. This is just to give us a view on how much packet traffic is moving in and out of whatever tile we're looking at. So we have a row, wherever it is, northeast, east, southeast, southwest, and west. MFM is the engine traffic. That's the most important stuff. BLK, that's bulk. That's for updating the CDM, the Common Data Manager packages. And then this is just the sum of them over here. And so, we're doing something like 75, depending on things, it gets hot in here. The processors slow down. What are we running at here? Oh, we're still running at 1 gig. That's as fast as these things can go. And we're doing something like 70 packets, 80 packets. That'll climb up to about 90 packets a second in and out in all 6 directions. In this case, because we're in the middle tile, so that's fully connected all the way around. And, is that pitiful? Compared to what? Nothing else has ever done this, in these specific design constraints. So who knows? And so it's doing 5 to 6 kilobytes a second, which seems pretty pitiful, both input and output in each of 6 directions. And, I would love that to be megabytes, or at least hundreds of kilobytes. And this is really I still think the single biggest thing that's going to limit the T2 tiles AER, average event rate, in the end is just our raw communication speed. And we'd love to look forward to a T3 tile that using some differential signals that could go much, much faster than all of this. But again, the point is, spring the bear traps, see what kind of failures we've got. Look at this. Friday, October 9th. Why is that going on? Why is that going on? Because the middle tiles, anything except for the tiles along the west edge, they never see the network. So they can't run network time. They have no idea what time it is. And that's a feature, once again, because, assuming the existence of coordinated global time is another form of synchronization, another form of coupling systems together that we don't want to do. Okay, well, anyway, so that's the packet viewer, and we also have, and then I will stop, sys class ITC packet. The new one is FIFOs. Yeah, okay. And the important point here, the last 2 rows, the last 2 columns, C drop and T drops is recording packet drops that the Linux kernel module had to toss stuff because it didn't have room in a buffer when a packet was coming through. C drops is current drops since the last time we looked at this FIFO file. T drops is the total number of drops that we've had since the thing booted or this was reset. And, the last number is all 0. And, that means we haven't seen any at all. Now, when I distribute new packages, the bulk channels, the bulk outbound, and the 2 of them, because there's 2 coprocessors. Each coprocessor covers 3 of the neighbors. We see bulk outbound packets dropped. But I was prepared for that, and the Common Data Manager has retry logic built into it. I have not yet caught a priority outbound or MFM inbound dealing with the specific buffers coming in. But we've got a better way to see it. We also have improved tracing in MFM-T2, which seems to be working a little bit better here. So that's a start, step by step. Okay, so we are re-entering the grid. And... 'cause, 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 ' Embracing failure. So I've already talked about this, and I'm taking a lot of time, so I'll skip over it. But yeah, the hallmark of it is how big are the plates. Those things are tightly coupled that do not have necessarily a lot of redundancy above the level of size and position of each atom within the plate. And so once the size and position become inconsistent, we're in trouble. But hey, robust first computing, at some level, because of the fact that we were doing distributed limited stuff, we were doing some of that. But now we're taking it to the next level. Robust finally. Okay, so that's about it. The goal for today was to get back into the tiles. Did that. Programmed the stuff, new syslabus file, curved displayers. We saw that. The other thing was for this time was Ulam 5 release preparations. Did some of that too. And folks, if anybody is out there, I mean, there aren't very many Ulam programmers in the universe, and I love you folks for even trying. But some folks have actually built pretty substantial code. I don't know if anybody's really working on their code now, but in the past, people have worked on fairly substantial stuff. I'm kind of committed to making a breaking change in C2D. That's the package, the standard library for dealing with two-dimensional coordinates, to deal with multiplication of coordinates. Because the way I had it designed was that the multiplication of two coordinates produced an integer, and it did the dot product, which does this times this plus this times that, and comes back with a scalar value. And especially as I've been doing the plate stuff, I never want that. I almost never want that. And instead, I want the multiplication of two coords to do multiply the x's, multiply the y's, and give me back a chord with the result. So I'd love to hear discussion about it. I brought it up on the chat, on the Gitter, and if anybody's got any issues, please let me know, but I'm probably going to do it otherwise. The goal for the next update, number one, I want Ulam code to actually see an event fail somehow. I mean, at the very least, it'll just get an inconsistent result. We'll have an evil tecton twin or something like that that actually happened. Or perhaps if we could do something smarter, we will. And to get Ulam 5, the code base, building on the canonical build farm. That's where you have to send code to make Ubuntu packages that make it easier to do. And last time I tried to do the Ulam 5 on the canonical build farm, which was over a year ago now, I couldn't get it to build. Let's figure out what that's about. And we've got yet another version of Psi. I will just show that rather than explain the details. I think you'll get the idea. And we'll end with that. Which one? Closer. Where the heck is the closer here? And now I've completely lost. I can't find my... All right, here we go. Thanks for coming, folks. Sorry I went so long. All right. So that's it. See you next time. I'm going to stay on the live stream. I'm just going to keep streaming. If people want to chit chat, I guess I'll go back to the waiting room. See you folks in 2 weeks. Thanks for stopping by.